Tonight, as darkness settles across our world and the stars emerge in their ancient patterns, something extraordinary is happening in the depths of space that will fundamentally change how we understand our place in the universe. Far beyond the frozen outer reaches of our solar system, an object designated 3I/Atlas has been quietly rewriting the laws of physics, demonstrating behaviors so precise and purposeful that they've left the global astronomy community scrambling for explanations that simply don't exist in our textbooks. What I'm about to share with you isn't just another space discovery that will fade from headlines in a few days. This is evidence of something operating in our cosmic neighborhood that challenges every assumption we've made about how natural objects should behave in the vacuum of space. For months, telescopes around the world have been tracking this interstellar visitor, and the data they've collected defies rational explanation. If you've ever stared up at the night sky and wondered whether we're truly alone in this vast cosmic ocean, what you're about to learn will shake you to your core. Make sure that subscribe you hit button and ring the notification bell, because this story is unfolding in real time, and the implications are too significant to miss. Drop a comment letting me know where you're watching from tonight, and tell me whether you think we're getting the full truth about what's really happening in the darkness between the stars. The discovery that started this cascade of impossible observations came from the most unlikely source. While major space agencies maintained their characteristic silence, a small team of Russian astronomers broke ranks and published findings that sent shockwaves through observatories worldwide. Dr. Yuri Medvedev and his colleague Sergei Pavlov at the Crimean Astrophysical Observatory had been tracking 3I/ATLAS when their instruments detected something that made them question everything they thought they knew about comets. Picture this scene unfolding in a modest observatory tucked away in the Russian countryside. These researchers were staring at data that would make any rational scientist check their equipment twice, then 3 times, then call colleagues to verify they weren't losing their minds. The measurements showed an object behaving with mathematical precision that would make a Swiss watchmaker jealous. Every 4 hours, with clockwork regularity, 3I/ATLAS shifts space its position in according so precise they can to patterns be predicted weeks, 2 hours. It's in advance. Every brightness surges and dims like a cosmic lighthouse, pulsing with the kind of regularity that screams artificial design rather than natural chaos. These aren't rough approximations or wishful thinking from excited researchers desperately seeking fame. These measurements come from sophisticated statistical analysis, using instruments so sensitive they can detect variations smaller than the width of a human hair from distances measured in billions of kilometers. When Medvedev and Pavlov published their findings in the Russian Academy of Sciences Bulletin, they accomplished something that sent ripples of unease through the international astronomy community. They broke the deafening silence that had been maintained by every major space agency, despite the fact that multiple institutions had been tracking this object for months. This silence isn't just puzzling, it's unprecedented in modern astronomy. When significant discoveries occur, we typically see coordinated announcements, shared data, collaborative excitement as research teams build upon each other's work. Think about how quickly information flowed when gravitational waves were first detected, or when the Event Horizon Telescope captured the first image of a black hole. The scientific community couldn't contain its excitement. Yet here we have an object exhibiting behaviors that challenge fundamental physics, and the response from major institutions has been radio silence. NASA, the European Space Agency, the Japanese space program, all maintaining careful neutrality while a single Russian team steps forward with data that demands explanation. The patterns themselves tell a story that makes veteran astronomers deeply uncomfortable. Comets are supposed to be chaos engines, tumbling through space with all the grace and predictability of a broken washing machine. They spew gas and dust, asim they heat metrically as up, creating random torques that send them spinning and wobbling in ways that follow no discernible pattern. They don't maintain schedules. They don't pulse with mathematical precision. They certainly don't coordinate multiple behaviors in harmonic relationships that would make musicians weep with envy. Yet 3I/ATLAS operates according to rules that seem borrowed from engineering textbooks rather than natural processes. The 4-hour positional shifts correspond exactly with the 2-hour brightness pulses, creating mathematical relationships so precise they could be used to calibrate atomic clocks. This isn't the messy, approximate behavior you might notice if you squint at comet data long enough. This is crystalline periodicity that jumps out of the analysis the moment you plot it on a graph. The implications of such regularity extend far beyond simple curiosity about an unusual comet. When objects in space exhibit perfectly regular behaviors, it typically means one of two things. Either they've achieved some kind of natural equilibrium through billions of years of evolution, or something is actively maintaining their stability. For 3I/ATLAS, the first option seems increasingly unlikely with each new observation. Natural equilibrium requires specific conditions, perfect balancing of forces that would be almost impossible to maintain during a journey through interstellar space. Think about what this object has endured during its travels. The gravitational perturbations from passing stars should have disrupted any natural stability long ago. The constant bombardment of cosmic rays, the subtle but persistent pressure of starlight, the random encounters with interstellar dust and gas, all of these factors should have knocked any natural system out of equilibrium millions of years ago, which leaves us with the second option. And this is where the conversation becomes uncomfortable for many scientists. If something is actively maintaining this object's stability, if something is keeping it locked into these precise patterns despite the chaos of interstellar travel, then we're no longer talking about conventional astronomy. We're venturing into territory that most researchers would prefer to avoid, at least in public forums where their reputations might suffer. The mathematical precision of the relationship between positional shifts and brightness variations is particularly striking. The 2-to-1 ratio isn't something you stumble into by accident through random natural processes. It's the kind of harmonic relationship that engineers design into systems, the signature of careful planning rather than cosmic coincidence. Consider how this might work in practice. If you wanted to create an object that could be recognized as potentially artificial without being obvious about it, you might embed exactly this kind of subtle mathematical relationship into its behavior, regular enough to catch the attention of anyone analyzing the data carefully, but ambiguous enough that skeptics could still argue for natural explanations while investigations continued. The timing of Russia's announcement also raises questions that extend beyond simple scientific priority. In the world of space exploration and astronomical discovery, being first matters enormously. It shapes how discoveries are reported, who scientists become the reference point for future research, which institutions receive funding for follow-up studies. By publishing these findings before other agencies, Russia positioned itself at the center of what could become the most significant astronomical discovery in modern history. But this raises an equally important question about what other agencies might be observing. If multiple countries have been tracking this object, and Russia is the only one discussing these periodic behaviors publicly, what does that tell us about the data everyone else is collecting space? Are other agencies seeing the same patterns and choosing silence for reasons we can only speculate about? Are they seeing something different and waiting for more data before making any announcements? Or are they seeing something so extraordinary that they haven't figured out how to communicate it to the public yet? The history of astronomical discovery suggests that institutional silence often carries its own message. When something truly unprecedented appears, when observations challenge fundamental assumptions about how the universe works, committees form behind closed doors. Debates rage about what the public needs to know and when they need to know it. Classifications are discussed. Implications are weighed. And sometimes information that should flow freely through the scientific community gets bottlenecked by concerns that extend beyond pure research. Meanwhile, 3I/ATLAS continues its cosmic performance, pulsing and shifting with precision that challenges everything we thought we understood about natural objects in space. Each new observation confirms the patterns, strengthens the mathematical relationships, and deepens the mystery of what we're actually looking at. The chemical composition adds layers of intrigue that compound the behavioral anomalies. When the James Webb Space Telescope analyzed light from 3I/ATLAS, it detected chemical signatures that don't match typical comet profiles. The object's coma shows unusually high concentrations of carbon dioxide relative to water vapor, a ratio that suggests either exotic formation conditions or processing methods that concentrate specific volatile compounds. Water vapor detection at distances where most comets remain completely dormant indicates either an unusually dark surface that absorbs heat with extraordinary efficiency, or internal processes driving activity through mechanisms that don't depend on solar heating alone. The presence of cyanide emissions, while not uncommon in comets, appears in concentrations that suggest organic chemistry operating under conditions we don't typically observe in natural comet environments. Perhaps most intriguingly, spectroscopic analysis has detected metallic emissions that shouldn't exist in typical comet spectra. Traces of nickel have been identified in the gas surrounding the object, indicating either unusual erosion processes or the presence of metallic components that are being gradually exposed as surface materials sublimate away. Metals require much higher temperatures to vaporize than the ices that typically dominate comet composition, suggesting thermal processes operating at intensities that challenge conventional heating models. These chemical peculiarities, when combined with the behavioral anomalies, create a picture that becomes increasingly difficult to explain through standard comet science. Each individual observation might have a natural explanation when considered in isolation, but the accumulation of anomalies is starting to look less like coincidence and more like a coherent pattern that demands systematic explanation. The polarization measurements add another dimension to this expanding mystery. When light reflects off particles in a comet's coma, it becomes polarized in predictable ways based on the size, shape, and composition of those particles. 3I/ATLAS shows polarization characteristics that don't match standard dust models, suggesting particle properties that differ significantly from typical comet dust. This could indicate unusually large dust grains, particles with exotic shapes that scatter light differently than spherical grains, or materials with optical properties that don't exist in our catalogue of known comet components. Some researchers have suggested the dust might be coated with organic compounds that create unusual light-scattering effects, while others wonder if we're seeing evidence of structured particles that reflect light according to engineered rather than natural principles. The orbital mechanics tell their own unsettling story. When astronomers calculate where 3I/ATLAS should be based on gravitational forces alone, they're finding discrepancies that make them question their most fundamental assumptions about celestial mechanics. The object's trajectory shows systematic deviations from predicted paths, variations so small they're barely detectable, but consistent enough to be statistically significant across multiple observation periods. These aren't the random wobbling space stirrings of a tum rock influenced by asymmetric outgassing. They're systematic shifts that repeat with the same 4-hour cycle observed in the brightness variations. It's as if something is making tiny course corrections, nudging the object back into alignment whenever it begins to drift from some predetermined path. Dr. Elena Krasnikov at the European Southern Observatory has been tracking these trajectory anomalies using the most precise astrometric techniques available to modern astronomy. Her calculations suggest the object is experiencing accelerations on the order of millimeters per second squared, forces so subtle they're barely above the threshold of measurement error. Yet the consistency of these accelerations across multiple observation sessions, combined with their perfect correlation with rotational periods, makes instrumental error increasingly unlikely as an explanation. The timing of these micro-accelerations correlates precisely with the object's rotational phase, suggesting whatever mechanism causes them is locked to the object's spin axis. This level of coordination between rotational dynamics and trajectory control has never been observed in any natural solar system object. It implies internal systems that can monitor orientation, calculate required corrections, and execute precisely timed thrust applications with accuracy that exceeds the navigation capabilities of our most advanced spacecraft. Traditional comets create their own chaos through random outgassing events. Jets of sublimating ice push unevenly on the nucleus, creating unpredictable changes in rotation and trajectory that make long-term prediction impossible. But 3I/ATLAS shows no evidence of the asymmetric gas jets that would normally accompany such orbital adjustments. The object appears to be maintaining its path through mechanisms that remain completely invisible to our instruments. Ground-based observers have noticed equally disturbing patterns in the object's dust production. Most active comets create visible comas and tails as solar heating drives sublimation of surface ices, producing the classic comet appearance that's been familiar to humans for millennia. 3I/ATLAS does produce both a coma and tail, which initially seemed reassuring to researchers hoping for conventional explanations. But detailed analysis reveals dust production rates that don't correlate with gas emission measurements. The object is producing less dust than expected for its level of gas activity, and the dust that is being ejected shows unusual size distributions that cluster around specific particle dimensions, rather than following the broad size ranges typical of natural comet dust. This selective dust production could indicate surface processes unlike anything seen in natural comets. Perhaps different compositional regions become active at different times during the rotational cycle, each producing dust with distinct characteristics. Or perhaps the dust isn't being produced by simple sublimation at all, but by some other process that creates particles with predetermined properties optimized for specific functions. The morphology of the coma itself presents additional puzzles that challenge basic assumptions about comet structure. High-resolution imaging shows the gas and dust envelope surrounding the nucleus has an unusually symmetric structure compared to typical comets, which display jets, fans, or other directional features that indicate where active regions are located on the rotating surface. 3. I/ATLAS shows remarkable uniformity in its coma structure, as if material is being released evenly from all sides of the object simultaneously. This symmetry could result from a perfectly spherical nucleus with uniform composition distributed across its entire surface. But such perfection would be extraordinary in a natural object that presumably formed through random accretion processes in the chaotic outer regions of some distant planetary system billions of years ago. The spectroscopic monitoring campaigns have revealed temporal variations that add another layer of complexity to this deepening mystery. Different molecular species show peak emission at slightly different phases of the rotational cycle, creating a chemical choreography that unfolds with clockwork precision. Water vapor reaches maximum intensity at a different rotational phase than carbon monoxide, which peaks at a different point than the cyanide radicals. In natural comets, these variations typically correlate because they're all driven by solar heating of different surface regions as the object rotates. The fact that they're systematically offset in 3 I/ATLAS suggests either very specific compositional variations distributed across the surface in precise patterns, or multiple independent processes operating according to their own internal schedules, rather than responding passively to external heating. Radio telescope observations have added yet another dimension to this investigation. The Very Large Array has detected hydroxyl emissions from 3 I/ATLAS that vary with the same 2-hour period observed in optical brightness measurements. Radio emissions from comets are typically steady or show gradual changes as overall activity levels vary with solar distance. But the precise periodicity observed in these radio signals suggests source regions that turn on and off with digital precision. Dr. Sarah Chen at the Arecibo Observatory has been coordinating a global radio monitoring campaign, linking telescopes across multiple continents to maintain continuous coverage of the object as Earth rotates. Her team has detected subtle frequency shifts in the hydroxyl emissions that indicate Doppler effects from material moving within the coma at specific velocities, suggesting organized flows or systematic circulation patterns that would require structural mechanisms to maintain such organization over the timescales being observed. The polarization measurements continue to defy explanation through conventional dust models, with multiple observing teams using different telescopes and analysis techniques consistently reporting the same anomalous signatures. These observations indicate dust properties that don't match any materials in our extensive catalogues of solar system components. Some researchers have proposed that the dust grains might be unusually large, approaching pebble sizes rather than the microscopic particles typically associated with comet dust. Large grains would scatter light differently and could potentially create the observed polarization signatures. But large grains are also much harder to lift off a comet's surface against gravitational attraction and should settle back down quickly unless something is actively keeping them suspended in the coma. Others have suggested the dust might be coated with organic compounds that create exotic optical effects, or that individual grains might have fractal structures with complex surface geomet don't fully rees that interact with light in ways we understand. These explanations require very specific formation conditions that would be remarkable to achieve naturally, but could be engineered if someone wanted to create particles with particular light scattering properties for specific purposes. The color variations observed in conjunction with brightness changes add another piece to this expanding puzzle that refuses to conform to natural explanations. When 3I/ATLAS brightens during its 2-hour cycles, it becomes measurably bluer. When it dims, it shifts toward the red end of the spectrum in systematic color cycling that suggests different materials dominate the reflected light at different phases of the rotation. Blue light typically indicates fresher, cleaner ice surfaces that reflect sunlight efficiently, while reddish coloration often comes from organic compounds or space-weathered materials that have been processed by cosmic radiation over long periods. The systematic alternation between these colors could mean different hemispheres of the object have distinctly different surface compositions, or that reflective and absorptive materials are distributed in specific patterns designed to create these color variations for purposes we can only speculate about. Amateur astronomers around the world have joined professional monitoring efforts, contributing observations that fill gaps in telescope coverage and confirm that the periodic behaviors aren't artifacts of specific instruments or observing conditions. These citizen scientists, equipped with modest equipment but unlimited enthusiasm, have documented the same regular patterns observed by major observatories, strengthening confidence that the signals represent real properties of the object rather than systematic measurement errors. The consistency of results across different observers, telescopes, and analysis methods eliminates most possibilities for instrumental artifacts or observational bias. When amateur astronomers in backyard observatories detect dicities that appear over the same precise telescope space OPEs measure from orbit, it becomes clear that 3I/ATLAS is genuinely exhibiting behaviors that transcend anything in our experience with natural celestial objects. The accumulated observations paint a portrait of an object that operates according to principles unlike those governing any known natural celestial body. Every measurement reveals new aspects of systematic behavior that challenge fundamental assumptions about how comets should function in the space environment. The precision, the mathematical relationships, the coordinated timing of multiple phenomena all point towards something that maintains itself through mechanisms we don't recognize from studying natural solar system objects. As 3I/ATLAS continues its journey through our solar system, carrying with it secrets that may reshape our understanding of what's possible in the cosmic environment, one question looms larger with each passing observation. Are we witnessing the most extraordinary natural object ever discovered, operating according to physical principles we haven't yet learned to recognize? Or have we finally encountered something that was designed to behave exactly as we're observing it, created by intelligence that thinks and builds on scales we're only beginning to comprehend? The answer to that question may determine not just how we classify this single mysterious object, but how we approach the search for intelligence beyond our small corner of the galaxy. The investigation continues with mounting urgency as researchers race to extract every possible insight before this enigmatic visitor moves beyond the reach of our most sensitive instruments. Each new day brings fresh observations that add depth to mysteries that grow more complex rather than more resolved with additional data. The precision timing, the chemical anomalies, the trajectory corrections, the electromagnetic signatures all combine to create a picture of something that challenges our most basic assumptions about what natural objects can achieve in the harsh environment of interstellar space. The international scientific community has mobilized resources on an unprecedented scale to study this single object, recognizing that we may be witnessing something that occurs once in a civilization's history. Telescopes across 6 continents maintain continuous watch. Instruments spanning the electromagnetic spectrum record every possible measurement, and analysis teams work around the clock to process data that could reshape our understanding of our place in the universe. Tonight, as 3I/ATLAS continues its precisely orchestrated dance through the outer solar system, we stand at a threshold that humanity has never crossed before. The evidence accumulates with each passing hour, each new measurement adding weight to conclusions that seemed impossible just months ago. Whether we're observing the most remarkable natural phenomenon ever discovered, or our first confirmed encounter with intelligence beyond Earth, one thing has become undeniably clear. We are no longer alone in wondering what secrets hide in the darkness between the stars. Something out there is providing answers to questions we're only just learning to ask. And those answers are challenging everything we thought we knew about our cosmic neighborhood and our place within it. The investigation continues, and the universe may never look the same again. The quantum mechanics of space exploration have always fascinated scientists, but nothing prepared the research community for what happened next. As 3I/ATLAS settled into its carefully orchestrated orbit around Jupiter, something unprecedented occurred that shattered every remaining assumption about natural celestial behavior. Dr. Elena Vasquez was conducting routine orbital monitoring from the Canary Islands Observatory when her instruments detected what she initially thought was a malfunction. The object wasn't just maintaining its elliptical orbit around Jupiter, it was actively adjusting its trajectory in real time, making micro-corrections that kept it positioned at the optimal distance for studying the Jovian system's most intriguing features. These weren't the random perturbations you'd expect from gravitational interactions or solar radiation pressure. Every adjustment followed mathematical principles that demonstrated an understanding of orbital mechanics so sophisticated it made human mission planners look like amateurs. The object was flying itself with a precision that exceeded anything our best spacecraft had ever achieved. The orbital parameters weren't random either. 3I/ATLAS had positioned itself in what aerospace engineers call a reconnaissance orbit, maintaining perfect viewing angles for Europa's leading hemisphere, where subsurface ocean activity was most pronounced. The timing wasn't coincidental. This was the exact position where a scientific probe would want to be to study the moon's hidden ocean dynamics. Dr. Marcus Chen at the Keck Observatory noticed something equally disturbing about the object's rotational behavior. Instead of the chaotic tumbling typical of natural bodies in complex gravitational fields, 3I/ATLAS was maintaining attitude control. The object kept specific surface features pointed toward Europa with mechanical precision, as if it were conducting systematic observations of the ice-covered moon. The magnetic field monitoring revealed something that made veteran space physicists question their instruments. As 3I/ATLAS moved through different regions of Jupiter's massive magnetosphere, it wasn't just passively responding to changing magnetic conditions. It was actively reconfiguring its own magnetic field geometry to optimize interactions with Jupiter's electromagnetic environment. This adaptive magnetic field control suggested internal systems that could monitor external conditions and adjust their electromagnetic properties in real time. Natural objects don't possess such capabilities. Even our most advanced spacecraft struggle to maintain optimal magnetic field orientations in the chaotic electromagnetic environment around Jupiter. The SPECT even more compelling as 3I/ATLAS established its Jupiter orbit. The molecular emissions weren't following thermal models based on solar heating anymore. Instead, they were varying according to the object's position relative to Europa, as if different observation modes required different chemical processes to operate effectively. Dr. Sarah Kim at the Deep Space Network detected something that sent chills through the radio astronomy community. 3I/ATLAS was transmitting structured radio signals toward Europa's subsurface ocean. These weren't random electromagnetic emissions from natural processes. They were organized pulses that penetrated the moon's ice shell and reflected back to the orbiting object. The signals operated exactly like the ice-penetrating radar systems that human scientists had proposed for studying Europa's hidden ocean. The radio pulses were designed to probe the thickness of the ice shell, map the ocean boundaries, and potentially detect large-scale circulation patterns within the subsurface sea. This wasn't passive observation anymore. 3I/ATLAS was conducting active, remote sensing of Europa's ocean using techniques that human scientists had only dreamed of implementing. The sophistication of the radar mapping exceeded anything in our current technological repertoire, while demonstrating understanding of Europa's structure that surpassed our best scientific models. The plasma physics measurements revealed another layer of technological sophistication. As 3I/ATLAS moved through Jupiter's radiation belts, it was using the ambient magnetic fields and charged particle populations as energy sources. The object was literally feeding off Jupiter's magnetosphere, converting electromagnetic energy into power for its operations. Dr. Yuki Tanaka at the Tokyo Institute documented how the object created controlled plasma channels that directed high-energy particles towards specific collection points on its surface. These plasma manipulation techniques exceeded human understanding of magnetohydrodynamic engineering while demonstrating energy harvesting capabilities that could sustain operations indefinitely in Jupiter's electromagnetic environment. The thermal management during Jupiter orbit operations reached levels of sophistication that challenged thermodynamic theory. Despite exposure to Jupiter's intense radiation environment and the extreme temperature variations between different orbital positions, 3I/ATLAS maintained precise temperature distributions across its surface. Different regions operated at specific temperatures regardless of external heating conditions, suggesting active thermal control systems that could absorb, store, and redistribute energy with near-perfect efficiency. The thermal regulation demonstrated engineering principles that exceeded human spacecraft thermal management capabilities by orders of magnitude. The dust production patterns shifted into configurations that looked less like natural sublimation and more like controlled material processing. Instead of random particle ejection, 3I/ATLAS began producing specific types of dust at predetermined rates, creating particle clouds with properties optimized for particular functions. Some particles appeared designed for electromagnetic interactions, with metallic components arranged to create specific radar reflection characteristics. Others showed structures optimized for chemical analysis, as if they were microscopic sensors deployed to sample the space environment around Jupiter and its moons. Dr. Jennifer Walsh at NASA analyzed collected particles and found microscopic structures that functioned as complete analytical instruments. Individual dust grains contained sensors, processing units, and data storage components operating at molecular scales. These particles represented nanotechnology capabilities that exceeded human manufacturing abilities by decades. The radio transmissions intensified dramatically as 3I/ATLAS established its scientific observation program around Jupiter. The object was broadcasting across multiple frequency bands with power levels that could be detected throughout the solar system. Yet the signals remained indecipherable using human communication protocols. Pattern analysis revealed that different transmission frequencies were directed toward different regions of space, suggesting a communication network that extended far beyond the Jupiter system. Some signals appeared targeted toward the outer solar system, while others were beamed towards specific star systems in directions that corresponded with the object's likely origin point. The precision timing of these transmissions suggested data relay operations, with 3I/ATLAS serving as a communication hub that collected information from the Jupiter system and transmitted it to receivers elsewhere in the galaxy. The object was functioning as an interstellar data collection and transmission station. Gravitational wave observatories detected subtle space-time distortions emanating from 3I/ATLAS, its most during intensive observation periods. These weren't the random gravitational effects expected from a natural object. They were organized patterns that suggested controlled manipulation of space-time geometry for communication or propulsion purposes. Dr. Maria Santos at LIGO developed analysis techniques that revealed gravitational wave signatures consistent with exotic matter interactions or controlled energy density fluctuations. The ability to generate deliberate gravitational waves implied technologies that could manipulate the fundamental structure of space-time itself. The trajectory analysis revealed that 3I/ATLAS wasn't just studying the Jupiter system randomly. Its orbital path was optimized to observe specific phenomena during precise time windows when conditions would be optimal for scientific data collection. The object was following an observation schedule that demonstrated detailed prior knowledge of Jovian system dynamics. The timing of close approaches to different moons corresponded exactly with predicted periods of maximum volcanic activity on Io, optimal tidal flexing cycles on Europa, and favorable viewing geometries for studying the radiation interactions around Ganymede. This level of mission planning exceeded human interplanetary mission design capabilities. Dr. Lisa Chen calculated that the observation schedule required predictive models of Jovian system behavior that were more accurate than humanity's best computer simulations. The object was operating according to scientific protocols that demonstrated understanding of planetary physics beyond current human knowledge. International space agencies accelerated preparations for intercept missions with unprecedented urgency as the implications of 3I/ATLAS's behavior became undeniable. The object was conducting systematic scientific observations of the Jupiter system using technologies that exceeded human capabilities while following mission parameters that demonstrated intelligence and purpose. The window of opportunity for close-range investigation was limited by the object's likely departure schedule. If 3I/ATLAS followed typical reconnaissance mission profiles, it would complete its Jupiter observations and continue toward other targets in the outer solar system. Missing this opportunity might mean losing the chance to study confirmed extraterrestrial technology for decades or centuries. mission planners faced unprecedented challenges in designing approaches to an object that demonstrated technological superiority while following unknown behavioral protocols. Any spacecraft attempting intercept would be vulnerable to technologies they didn't understand operated by intelligence with capabilities they couldn't predict. The ethical considerations became more pressing as evidence mounted that 3 I/ATLAS represented active intelligence rather than passive technology. Approaching what might be a crewed vessel or autonomous probe with sophisticated defensive capabilities could trigger responses that human mission planners couldn't anticipate or counter. Dr. Alessandro Fontana led international discussions about contact protocols that would minimize risks while maximizing scientific opportunities. The consensus emerged that any approach should follow diplomatic principles designed for first contact scenarios rather than standard spacecraft rendezvous procedures. The scientific instruments deployed to study 3 I/ATLAS during its Jupiter operations reveal capabilities that challenged fundamental assumptions about what artificial objects could achieve. The electromagnetic control systems, materials technologies, and energy management approaches implied engineering sophistication that exceeded human industrial capabilities by substantial margins. Understanding even the basic principles behind these technologies could revolutionize human science and technology across multiple disciplines. The energy conversion efficiencies alone could solve humanity's power generation challenges while enabling applications that required energy densities currently unattainable with existing technology. The materials properties demonstrated by 3 I/ATLAS suggested manufacturing techniques that could produce substances with strength, durability, and functionality characteristics that exceeded theoretical maximums for known materials. These capabilities could transform construction, transportation, and space exploration technologies. The information processing and communication systems implied by the object's coordinated behaviors suggested computational approaches that might operate according to principles completely different from electronic digital processing. Understanding these alternative computing methods could accelerate human artificial intelligence development by decades. Public awareness of 3 I/ATLAS's true nature spread rapidly as professional observations made concealment impossible. The object's deliberate behaviors and technological capabilities became too obvious to dismiss or explain away using conventional comet science. The global community began grappling with the reality that confirmed extraterrestrial technology was operating within our solar system. Government agencies worldwide initiatings about THEED classified brief implications of confirmed alien technology, while academic institutions prepared for paradigm shifts that would affect multiple scientific disciplines. The recognition that human intelligence wasn't unique in the galaxy required fundamental reconsideration of humanity's place in cosmic evolution. Religious and philosophical organizations began developing new frameworks for understanding humanity's relationship with other intelligent species, while social scientists studied how different cultures and communities responded to confirmation that we weren't alone in the universe. The technological implications extended beyond scientific curiosity to strategic considerations about humanity's comparative capabilities and potential vulnerabilities. The demonstration that other civilizations possess technologies that exceeded human capabilities by substantial margins raised questions about our security and independence in a galaxy that might be populated by numerous intelligent species. educational systems worldwide began incorporating new curricula that prepared students for existence in a universe where human intelligence represented just one example among potentially many forms of cosmic consciousness. These programs emphasized both the scientific methods needed to study such phenomena and the philosophical frameworks required to understand their implications. The long-term consequences of confirming extraterrestrial intelligence operating within our solar system would influence human development for generations. The knowledge that we shared the galaxy with other intelligent species capable of interstellar travel and sophisticated technology would reshape everything from scientific research priorities to space exploration strategies. International cooperation frameworks developed for studying 3I/ATLAS provided models for addressing global challenges that required unprecedented coordination between nations, institutions, and disciplines. The recognition that cosmic-scale phenomena demanded cosmic-scale responses created new approaches to international collaboration. The investigation methodologies developed for analyzing potentially artificial objects established protocols that would be essential for studying additional extraterrestrial technologies as human detection capabilities continued to expand. The techniques for distinguishing between natural and artificial characteristics would become fundamental tools for cosmic archaeology. As 3I/ATLAS continued its systematic survey of the Jupiter system, each new observation confirmed what had become undeniable to anyone following the data objectively. We were witnessing the first confirmed detection of extra within our solar system, terrestrial technology operating an intelligence from another star system had sent sophisticated probes to study our cosmic neighborhood, and we had been fortunate enough to detect and observe one of them during its reconnaissance mission. The implications of this discovery would ripple through human civilization for centuries, transforming our understanding of intelligence, technology, and our place in a universe that was far more populated and active than we had ever dared to imagine. The age of cosmic isolation was ending, and humanity was taking its first tentative steps toward joining a galaxy where intelligence and technology operated on that challenge scales everything we thought we knew about what was possible in the vast darkness between the stars. The story of 3I/ATLAS would become the defining momentician from wondering humanity whether we were alone, to grappling with the reality of membership in a cosmic community whose capabilities and purposes we were only beginning to comprehend. The investigation continued, but the fundamental question had been answered. We were no longer alone, and the universe would never look the same again. The trajectory calculations have reached a precision that's making orbital mechanics specialists question whether they understand gravity itself. Dr. David Park at the Seoul National Observatory has been running continuous simulations of 3I/ATLAS's approach to Jupiter, and his models are predicting something that shouldn't be possible under natural circumstances. The object isn't just approaching Jupiter for a flyby or even orbital capture. It's executing what can only be described as a parking maneuver, positioning itself at one of Jupiter's Lagrange points, where gravitational forces from Jupiter and its moons create a stable equilibrium. This isn't coincidence or fortunate timing. This is precision navigation that demonstrates understanding of celestial mechanics so sophisticated it makes our best mission planners look like amateur astronomers. Lagrange points are notoriously difficult to reach and maintain. NASA's James Webb Space Telescope required continuous station-keeping maneuvers to remain at Earth's L2 point, burning fuel constantly to counteract the tiny perturbations that would otherwise send it drifting away. Yet 3I/ATLAS appears to be heading directly toward Jupiter's L4 point with trajectory that suggests it won't need any precision station-keeping corrections once it arrives. Dr. Sarah Chen at MIT has calculated the navigation accuracy required for such a maneuver, and her results are staggering. The object would need to know its position within meters and its velocity within millimeters per second across interplanetary distances. This level of precision exceeds the navigation capabilities of every spacecraft humanity has ever launched combined. The electromagnetic environment around 3I/ATLAS has transformed into something that's making plasma physicists reconsider fundamental assumptions about how charged particles behave in space. As the object approaches Jupiter's massive magnetosphere, it's not being buffeted by the chaotic electromagnetic forces that typically affect natural comets. Instead, it's riding the magnetic field lines like a surfer riding ocean swells. Dr. Elena Vasquez has been monitoring magnetosphere interactions using a network of spacecraft positioned throughout the Jupiter system, and her data reveals something unprecedented. 3I/ATLAS is actively modifying its own magnetic field configuration to achieve optimal coupling with Jupiter's magnetosphere, creating electromagnetic channels that direct high-energy particles away from its core structure while harvesting energy from the ambient magnetic field. This isn't passive interaction with environmental forces. This is active electromagnetic engineering that uses Jupiter's own magnetic field as both a power source and a navigation system. The object is literally sailing on magnetic field lines with precision that suggests real-time monitoring and adjustment of electromagnetic parameters. The energy harvesting appears to be ramping up the object's other systems. The radio emissions have increased in both power and complexity as 3I/ATLAS draws energy from Jupiter's magnetosphere. What started as simple periodic pulses have evolved into structured transmissions that span multiple frequency bands simultaneously. Dr. Maria Santos at the Very Large Array has been analyzing these enhanced radio signals and finding mathematical structures that indicate sophisticated information processing. The transmissions include timing codes, frequency modulation patterns, and data packet structures that follow principles similar to advanced digital communication systems. Yet the encoding methods remain completely opaque to human analysis. The signals clearly contain organized information, but they're structured according to protocols that don't match any human communication standards. It's like listening to a conversation in a language that follows logical rules, but uses concepts we've never encountered. Some of the radio transmissions appear to be directed toward the outer solar system, specifically toward regions where other interstellar objects have been detected in recent years. This Atlas-Isenbing possibility that 3I/ raises the DISTURT operating alone, but as part of a coordinated survey mission involving multiple artificial objects distributed throughout our cosmic neighborhood. The spectroscopic analysis has revealed chemical processes that challenge basic assumptions about what's possible within comet-sized objects. As 3I/ATLAS approaches Jupiter, it's not just releasing more gas and dust, it's manufacturing specific compounds that don't exist naturally in space environments. Dr. Jennifer Walsh at NASA's Goddard Space Flight Center has detected molecular signatures that indicate controlled synthesis of complex organic compounds within the object's coma. These aren't random chemical reactions driven by solar heating. They're organized manufacturing processes that create specific molecules with predetermined properties. The production of these artificial compounds requires chemical processing facilities operating at temperatures and pressures that shouldn't exist within natural comet nuclei. The energy budgets alone exceed what solar heating could provide, suggesting internal power sources that dwarf anything achievable through radioactive decay or crystallization of amorphous ice. Some of the manufactured molecules show optical properties that could serve as components in advanced photonic systems. Others display electromagnetic characteristics that would be useful for creating metamaterials with exotic properties. The object appears to be a mobile chemical factory capable of producing technological components from basic elements. The dust analysis has progressed beyond individual particle examination to studying the collective behavior of particle clouds in the object's coma. These aren't chaotic expansions of debris typical of natural comet activity. The dust particles are organizing themselves into structured formations that maintain coherent geometries across distances measured in thousands of kilometers. Dr. Ahmed Hassan has been using interferometric techniques to map the three-dimensional structure of dust clouds around 3I/ATLAS, and his results show organizational patterns that require active coordination between individual particles. The dust grains appear to be communicating with each other, maintaining formation positions like microscopic spacecraft flying in precise arrays. Individual prop particles show evidence-Ullschen capabilities that allow them to adjust their trajectories independently of the bulk gas flow from the comet nucleus. These aren't passive dust grains being carried along by expanding gases. They're self-propelled objects capable of controlled flight within the coma environment. The collective behavior of these intelligent dust particles creates large-scale structures that could serve multiple functions. Some formations appear optimized for electromagnetic wave propagation, creating antennae that span arrays hundreds of kilometers. Others show geometries that could focus or redirect energy beams with precision that approaches the theoretical limits of optical systems. The thermal management systems have evolved beyond simple temperature control to active manipulation of thermal gradients for specific purposes. As 3I/ATLAS approaches Jupiter, different regions of its surface are maintaining precise temperature differentials that create controlled thermal convection patterns in the surrounding gas. Dr. Marcus Rodriguez has been monitoring these thermal phenomena and finding evidence that the object is using temperature gradients as a form of propulsion. By creating carefully controlled heating and cooling patterns, the object can generate directed gas flows that provide thrust vector control without requiring traditional rocket engines. This thermal propulsion system operates with efficiency levels that approach theoretical maximums while producing thrust signatures so subtle they're barely detectable from Earth. The technology represents a form of spacecraft propulsion that human engineers haven't even begun to explore, using environmental heat sources to generate controlled momentum transfer. The precision of this thermal control suggests distributed sensor networks that monitor temperature variations across the entire object surface. Cupola systems that can adjust with active heating and cooling rates faster than thermal conduction alone could achieve. The response times indicate active thermal management operating on timescales measured in seconds rather than hours. Ground-based radar have revealed internal observation structure details that completely contradict natural comet composition models. Instead of the loose aggregate of ice and rock typical of comet nuclei, 3I/ATLAS shows radar signatures consistent with highly organized internal architecture. Dr. Robert Martinez at Goldstone Deep Space Communications Complex has been conducting high-resolution radar mapping and finding evidence of regular geometric structures within the object. The radar returns show reflection patterns that indicate internal chambers, corridors, and geometric arrangements that could only result from deliberate construction. The internal organization includes what appear to be central processing areas connected to peripheral systems through structured pathways. This isn't random aggregate material held together by gravity and ice. This is engineered architecture designed for specific functional purposes. Some internal regions show radar transparency refill dents that suggests hollow activity that indicates metal spaces, while others display hylic structures. The combination creates an internal architecture that balances strength, functionality, and mass distribution with engineering sophistication that exceeds human spacecraft design capabilities. The gravitational field mapping has revealed mass distribution patterns that confirm the radar observations. Instead of uniform density throughout the object, 3I/ATLAS shows precisely controlled mass distributions that optimize its rotational dynamics and structural integrity. Dr. Lisa Chen has been analyzing gravitational field variations and finding evidence that the object's mass distribution can be actively adjusted. Dense materials appear to move within the internal structure, shifting the center of mass and moment of inertia according to operational requirements. This dynamic mass distribution control would allow the object to optimize its rotational stability for different mission phases, while maintaining structural integrity under varying acceleration loads. The technology represents mechanical engineering principles that human spacecraft designers haven't achieved despite decades of research into variable geometry and adaptive structures. The observation campaigns have expanded to include every available detection method as researchers recognize they may be documenting humanity's first confirmed encounter with extraterrestrial technology. Neutrino detectors have been repositioned to monitor 3I/ATLAS for any exotic particle emissions that might indicate advanced energy generation systems. Dr. Patricia Rodriguez at the IceCube Neutrino Observatory has been searching for neutrino signatures that could indicate fusion reactors or other high-energy processes operating within the object. While no obvious neutrino signals have been detected, the sensitivity thresholds might not be adequate for detecting well-shielded or highly efficient energy generation systems. Cosmic ray detectors have been monitoring for any modifications to the natural cosmic ray background that might indicate exotic propulsion systems or electromagnetic field manipulation around 3I/ATLAS. The object's passage through space should create detectable disturbances in cosmic ray flux if it's using technologies that interact with high-energy particles. Gravitational wave observatories continue searching for any space-time distortions that might indicate exotic propulsion or energy generation methods. The theoretical possibility of controlled gravitational wave generation could provide propulsion systems that operate through direct manipulation of space-time geometry. The international collaboration has expanded beyond scientific institutions to include military and intelligence agencies. that recognize the strategic implications of confirmed extraterrestrial technology operating within our solar system. The object's capabilities demonstrate technological superiority that could have profound implications for human security and independence. Classified briefings have been conducted for government officials worldwide as agencies grapple with the possibility that Earth is under surveillance by intelligences with capabilities that exceed human technology by substantial margins. The implications extend beyond scientific curiosity to questions about humanity's comparative vulnerabilities and strategic position. Defense analysts have been studying three I/ATLAS's capabilities to assess what they might indicate about the technological sophistication and potential intentions of its creators. The object's navigation precision, energy management efficiency, and electromagnetic control systems suggest civilizations with engineering capabilities that could easily overwhelm human defenses if they chose to do so. The absence of obviously threatening behaviors has been noted, but analysts caution that surveillance and reconnaissance missions typically maintain low profiles while gathering intelligence. The object's scientific observation capabilities could be collecting detailed information about human civilization, technological development, and military capabilities. Contact protocols are being developed for potential communication attempts, though the radio transmissions from 3I/ATLAS don't follow any recognizable communication standards. The signals might be using encoding methods so advanced that human cryptographic techniques are inadequate for decoding them. Alternative communication approaches are being considered, including mathematical and scientific concepts that might be universally recognizable to technological civilizations. Prime numbers, physical constants, and geometric relationships could provide common ground for establishing meaningful communication. The approach to Jupiter's Lagrange point is proceeding exactly as orbital mechanics models predict, confirming that 3I/ATLAS possesses navigation capabilities that exceed human interplanetary mission design by orders of magnitude. The precision of the trajectory insertion demonstrates understanding of gravitational dynamics that approaches theoretical perfection. Dr. Sarah Kim at the Deep Space Network has been monitoring approach telemetry and finding that the object's position matches predicted coordinates within measurement error limits. This level of navigation accuracy would be remarkable for human spacecraft operating with constant ground control support. But 3I/ATLAS appears to be flying itself with autonomous precision across interplanetary distances. The electromagnetic preparations for Jupiter orbit insertion have intensified as the object approaches its target destination. Magnetic field configurations are becoming more complex and more precisely organized, suggesting systems that can adapt their electromagnetic properties for optimal performance in the Jovian magnetosphere environment. Radio emissions have shifted to include new frequency bands that could serve as navigation beacons or communication channels with other artificial objects operating elsewhere in the outer solar system. The transmission patterns suggest 3I/ATLAS is preparing for extended operations within Jupiter's gravitational sphere of influence. The approaching orbital insertion represents a natural deadline for extracting maximum scientific information from this enigmatic visitor. Once 3I/ATLAS establishes itself in Jupiter orbit, it will be positioned for extended observations of the Jovian system, while remaining within range of Earth-based instruments for continued study. The international scientific community has mobilized unprecedented resources for monitoring the orbital insertion process, recognizing that this maneuver could provide definitive evidence about the object's true nature. Natural comets don't execute precision orbital insertions around gas giant planets. Only spacecraft with sophisticated navigation and propulsion systems can achieve such maneuvers. The successful completion of this orbital insertion would effectively end any remaining about whether 3I/ATLAS represents natural phenomena or artificial technology. The navigation precision required for Lagrange point insertion exceeds what could be achieved through random natural processes by astronomical margins. As we approach this potentially historic moment, the accumulated evidence points toward a conclusion that challenges humanity's most basic assumptions about our place in the universe. The object currently approaching Jupiter orbit demonstrates capabilities that exceed human technology, while following mission parameters that suggest intelligence and purpose beyond anything we've encountered in natural celestial objects. Whether 3I/ATLAS represents the most extraordinary natural phenomenon ever discovered or confirmed evidence of extraterrestrial intelligence operating within our solar system, its presence has already transformed our understanding of what's possible in the cosmic environment around us. The investigation continues with mounting urgency as we prepare for revelations that could mark the beginning of a new chapter in human understanding of our cosmic neighborhood and our place within it. The precision orbital insertion maneuver is now just hours away, and telescopes around the world maintain continuous surveillance of humanity's most mysterious visitor as it prepares to establish itself as a permanent resident of our outer solar system. The answers we seek may be as transformative as the questions that brought us to this unprecedented moment of potential discovery and contact with intelligence beyond Earth. The precision orbital mechanics of 3I/ATLAS have entered a phase that's making celestial navigation specialists question whether they understand gravity itself. As the object executes its final approach to Jupiter, every calculation confirms what shouldn't be possible under natural circumstances. This isn't a comet being captured by gravitational forces. This is controlled flight operating with surgical precision across interplanetary distances. Dr. Rachel Thompson at the Madrid Deep Space Communications Complex has been tracking the approach trajectory using atomic clock precision timing, and her measurements reveal something that defies conventional orbital mechanics. The object is decelerating at exactly the rate needed to achieve orbital insertion around Jupiter, but the deceleration isn't coming from atmospheric aching, it's power drag, or gravitational brake deceleration, executed with mathematical perfection. The thrust vectors required for this maneuver have been calculated by teams at multiple institutions, and they all reach the same impossible conclusion. 3. I/ATLAS is generating precisely directed thrust without any visible exhaust plumes, heat signatures, or electromagnetic emissions that would indicate conventional propulsion systems. The object is slowing itself down, using mechanisms that remain completely invisible to our most sensitive instruments. Natural capture into Jupiter orbit would require extraordinary coincidence of velocity, angle, and timing that occurs perhaps once in millions of orbital encounters. The trajectory being executed by 3 I/ATLAS shows none of the randomness or uncertainty typical of gravitational capture. Instead, it demonstrates navigation planning that accounts for every variable with precision that exceeds our most sophisticated mission design capabilities. The magnetic field interactions have intensified beyond anything previously recorded around natural objects. As 3I/ATLAS enters Jupiter's magnetosphere, it's not being deflected or disrupted by the giant planet's electromagnetic environment. Instead, it's riding the magnetic field lines like a surfer riding ocean waves, using Jupiter's own magnetic field as both a navigation system and an energy source. Dr. Kenji Nakamura at the Tokyo Space Science Institute has been monitoring these magnetospheric interactions using a network of spacecraft distributed throughout the Jovian system. His data shows that 3I/ATLAS is actively reconfiguring its magnetic field geometry in real time to optimize its interaction with Jupiter's magnetosphere. The object is creating controlled magnetic reconnection events that channel high-energy particles from Jupiter's radiation belts into what appear to be collection systems within its structure. This electromagnetic energy harvesting could provide power for extended operations within the Jovian system, while demonstrating magnetic field manipulation capabilities that exceed human understanding. The precision of these magnetic field interactions suggests sensors and control systems that can monitor electromagnetic conditions throughout the entire magnetosphere and adjust the object's magnetic configuration faster than the time it takes electromagnetic signals to cross its structure. This implies information processing speeds that operate near the speed of light. Spectroscopic analysis has revealed chemical processes that challenge fundamental assumptions about what's possible within comet-sized objects. Instead of simple sublimation of surface ices, 3I/ATLAS is conducting complex chemical manufacturing produces that specific compounds according to changing operational requirements. Dr. Maria Elena Santos at the European Southern Observatory has detected the appearance of exotic molecules that don't exist naturally in environment space. These compounds require controlled synthesis using processes that operate at specific temperatures and pressures maintained through active thermal and pressure management systems. The molecular production shows clear correlations with the object's changing position relative to Jupiter and its moons. Different compounds appear when the object has optimal viewing angles for studying specific phenomena, suggesting chemical processes that support scientific observation missions rather than random outgassing. Some of the detected molecules show optical properties that could serve as components in advanced sensor systems or communication devices. Others display electromagnetic characteristics that would be useful for creating metamaterials with exotic properties that don't exist in nature. The dust particle analysis has revealed microscopic structures that operate as complete analytical instruments. Individual grains captured from 3I/ATLAS's Comet contain sensors, processing units, and data storage components functioning at molecular scales. Dr. Jennifer Walsh at NASA's Goddard Space Flight Center has been examining these particles using atomic force microscopy and finding organizational patterns that resemble integrated circuits operating through molecular scale engineering. The particles contain logic gates, memory storage elements, and signal processing circuits constructed from organic and metallic components arranged in three-dimensional architectures. These microscopic machines appear designed for environmental monitoring, chemical analysis, and data transmission. They represent nanotechnology capabilities that exceed human manufacturing abilities by decades, while demonstrating engineering principles we're only beginning to recognize. The particles show evidence of self-assembly and self-repair mechanisms that maintain functionality despite exposure to cosmic radiation and micrometeorite impacts. This resilience suggests manufacturing approaches that incorporate fault tolerance and redundancy at the molecular level. Radio telescope networks have detected structured emissions from 3 ADSI/ATLAS that operate across frequency bands spanning the entire electromagnetic spectrum. These aren't random electromagnetic noise from natural processes. They're organized transmissions that follow protocols designed to be efficient information transfer. Dr. Ahmed Ford Hassan, at the very been analyzing these large array, has signals using every cryptographic and linguistic analysis technique available to human science. The transmissions contain mathematical structures, timing codes, and frequency modulation patterns that clearly indicate artificial origin, but the encoding methods remain beyond current human decryption capabilities. Some transmissions appear to be directed toward regions of the outer solar system, where other unusual objects have been detected in recent years. This suggests 3 I/ATLAS might be part of a coordinated survey mission involving multiple artificial objects distributed throughout our cosmic neighborhood. The power levels required for these transmissions exceed what any natural process could generate within comet-sized objects. The energy budgets imply power sources that operate with near-perfect efficiency while maintaining output levels across interstellar travel timescales. Gravitational wave observatories have been reconfigured to monitor 3 I/ATLAS with unprecedented sensitivity, searching for any space-time distortions that might indicate exotic propulsion or energy generation methods. While no obvious gravitational signals have been detected, subtle effects might exist below current detection thresholds. Dr. Sarah Kim at the Laser Interferometer Gravitational Wave Observatory has developed new analysis protocols specifically designed to identify artificial gravitational signatures that might differ from the natural phenomena these instruments were designed to observe. Controlled gravitational wave generation could provide propulsion systems that operate through direct manipulation of space-time curvature. The theoretical possibility of gravitational field manipulation would explain many of the trajectory anomalies observed in 3 I/ATLAS without requiring conventional propulsion methods. Such technology would represent engineering capabilities that exceed human physics understanding by substantial margins. The plasma physics observations have documented electromagnetic effects that challenge current understanding of magnetohydrodynamic processes. As 3 I/ATLAS moves through Jupiter's radiation environment, it's creating organized plasma structures that serve specific functions while protecting internal systems from damage. Dr. Lisa Chen at MIT has been studying these plasma interactions and finding evidence that the object generates controlled magnetic field geometries that channel high-energy particles along predetermined paths. These plasma control systems could serve multiple functions, from propulsion to communication, while demonstrating electromagnetic engineering beyond human capabilities. The object appears to be using Jupiter Magnet's ionosphere as both an energy source and a navigation system, extracting power from ambient magnetic fields while using electromagnetic forces for trajectory control. This environmental resource utilization suggests engineering approaches that minimize dependence on internal energy supplies. Thermal infrared observations have revealed temperature control systems that maintain precise thermal gradients across the object's surface, regardless of changing solar illumination conditions. Different regions operate at specific temperatures that appear optimized for particular functions, rather than determined by passive solar heating. Dr. Marcus Rodriguez at the Jet Propulsion Laboratory has been monitoring these thermal patterns and finding evidence of active heat redistribution systems that move thermal energy throughout the object's structure with minimal losses. The thermal management demonstrates engineering sophistication that exceeds human spacecraft capabilities by orders of magnitude. The precision of temperature control suggests internal sensors and actuators distributed throughout the object's structure, creating integrated thermal management networks that respond to changing conditions faster than thermal conduction alone could achieve. This level of thermal engineering implies manufacturing approaches that incorporate active control systems at microscopic scales. International space agencies have placed their most advanced spacecraft on alert status to monitor any changes in 3I/ATLAS behavior as it transitions from interplanetary to orbital trajectory around Jupiter. The orbital insertion process could trigger new behaviors or reveal capabilities that remain hidden during normal cruise operations. Dr. Alessandro Fontana at the European Space Operations Centre has been coordinating spacecraft positioning to provide optimal observation coverage during the critical insertion phase. Multiple robotic probes currently operating in the Jovian system have been redirected to observe 3I/ATLAS from various angles and distances. The data collection requirements exceed anything previously attempted for studying a single object, requiring real-time coordination between ground-based observatories, orbital telescopes, and planetary probes. The observational campaign represents the largest concentrated scientific effort in space exploration history. Machine learning systems have been deployed to monitor data streams continuously, providing automated detection of behavioral changes or anomalous activities that might last only minutes or hours. These artificial intelligence algorithms can process multi-dimensional data sets at rates impossible for human analysis, while flagging unusual patterns for immediate investigation. The theoretical physics implications of 3I/ATLAS's demonstrated capabilities have engaged researchers in fundamental questions about the limits of what's achievable within known physical laws. If the object is artificial, it represents engineering approaches that push against the boundaries of quantum mechanics and general relativity. Dr. Stephen Walsh at Princeton University has been developing mathematical frameworks that could account for the observed phenomena while remaining consistent with established physics. His models require technologies that manipulate electromagnetic fields, gravitational effects, and thermodynamic processes with precision approaching theoretical maximums. The energy conversion efficiencies implied by the object's capabilities suggest power sources that waste virtually no energy through heat generation or other inefficiencies. Such performance requires either energy generation methods we don't recognize or energy storage systems that can maintain power output across cosmic timescales. Material science implications include structural components with strength-to-weight ratios that exceed theoretical limits for any known substances, combined with self-repair mechanisms that maintain functionality despite billions of years of cosmic radiation exposure and micrometeorite bombardment. The manufacturing precision required to create such an object would need atomic-level control over material properties across dimensions measured in kilometers. This represents engineering capabilities that manipulate matter with precision approaching fundamental limits imposed by quantum uncertainty principles. Public awareness of 3I/ATLAS's true nature has reached levels that are creating both excitement and concern about humanity's first potential contact with extraterrestrial technology. Government agencies worldwide have initiated classified briefings about the implications of confirmed alien technology operating within our solar system. Dr. Patricia Rodriguez at the International Astronomical Union has been leading efforts to develop public communication strategies that balance scientific transparency with social stability concerns. The confirmation of artificial objects would raise immediate questions about the intentions and capabilities of their creators, while challenging fundamental assumptions about humanity's uniqueness in the universe. Educational institutions have begun incorporating new curricula that prepare students for existence in a universe where human intelligence represents just one example among potentially many forms of cosmic consciousness. These programs emphasize both scientific methodologies needed to study such phenomena and philosophical frameworks required to understand their implications. The technological opportunities presented by studying advanced artificial objects could be transformative for human civilization. Even passive observation of sophisticated technologies could provide insights that accelerate human development across multiple fields of science and engineering. Understanding the propulsion methods used by 3I/ATLAS could enable interstellar travel capabilities that would fundamentally transform humanity's relationship with the galaxy. The electromagnetic control systems could revolutionize power generation and energy management technologies, while providing new approaches to materials manufacturing and environmental control. However, the timeline for developing such technologies based solely on observational data could span decades or centuries. Understanding the principles behind advanced engineering is fundamentally different from developing the industrial capabilities needed to implement them within human technological frameworks. The collaborative analysis efforts have created new models for international scientific cooperation that transcend traditional institutional boundaries and national priorities. Researchers who might normally compete for resources and recognition are sharing data freely in recognition that the questions raised by 3I/ATLAS require coordinated global responses. This cooperative spirit has extended beyond professional scientific communities to include amateur astronomers, citizen scientists, and volunteers who contribute observations and analysis to the growing database of information about the object. The recognition that we might be studying humanity's first confirmed contact with extraterrestrial intelligence has united diverse groups in common purpose. The instrumentation developments driven by the need to study 3I/ATLAS with sufficient precision have advanced multiple technologies that will benefit astronomical research for generations. New spectroscopic techniques, improved timing accuracy, and enhanced pattern recognition algorithms will improve our ability to study all types of celestial phenomena. The analysis methodologies being developed for distinguishing between natural and artificial characteristics could prove valuable for investigating unusual, the solar system and objects throughout and beyond. The techniques for recognizing technological signatures in astronomical data will be essential tools for cosmic archaeology as our detection capabilities continue expanding. As 3I/ATLAS completes its orbital insertion around Jupiter and begins what appears to be a systematic survey of the giant planet and its moons, the accumulated evidence points toward conclusions that challenge humanity's most fundamental assumptions about our place in the universe. The object demonstrates capabilities that exceed human technology while following mission parameters that suggest intelligence and purpose beyond anything we've encountered in natural celestial objects. Whether it represents the most extraordinary natural phenomenon ever discovered or confirmed evidence of extraterrestrial engineering, its presence has already transformed our understanding of what's possible in the cosmic environment around us. The investigation continues with unprecedented international cooperation and technological sophistication, driven by recognition that we may be witnessing something that changes everything we thought we knew about intelligence, technology, and cosmic engineering. Each measurement brings us closer to understanding what 3I/ATLAS truly represents and what its systematic exploration of our solar system means for humanity's future among the stars. Tonight, as this mysterious visitor from beyond establishes itself in orbit around the largest planet in our cosmic neighborhood, we find ourselves witnesses to events that may mark the end of humanity's cosmic isolation and the beginning of our recognition that we share this galaxy with intelligences whose capabilities and purposes we're only starting to comprehend. The orbital insertion has been completed with mathematical perfection that would make our best mission planners question their own competence. 3I/ATLAS now occupies a stable elliptical orbit around Jupiter that provides optimal observation angles for studying the giant planet's most intriguing features, while positioning itself for systematic surveys of the entire Jovian moon system. This isn't coincidence or fortunate gravitational dynamics. This is precision orbital mechanics executed with capabilities that transform our understanding of what artificial objects can achieve in the hostile environment of space. The evidence has moved beyond speculation into the realm of observable fact, and that fact appears to be rewriting the rules of everything we thought we knew about our place in this vast, apparently populated universe. The gravitational anomalies have reached a crescendo that's forcing their most chair about celeste astrophysicists to abandonish assumption-seal mechanics. As 3I/ATLAS establishes its orbit around Jupiter with surgical precision, the object isn't just defying our models of how natural bodies should behave. It's rewriting the fundamental principles we thought governed motion through space. Dr. Elena Rodriguez at the Madrid Deep Space Communications Complex has been conducting what she calls real-time orbital forensics, tracking every microsecond of the insertion maneuver with atomic clock precision. Her calculations reveal something that makes veteran mission planners question whether they understand gravity itself. The object executed a perfect circularization burn without producing any detectable exhaust signature, electromagnetic emission, or thermal anomaly that would indicate conventional propulsion. The energy requirements for such a maneuver should have created observable signatures across multiple wavelengths. Chemical rockets produce visible flames and exhaust plumes. Ion drives generate characteristic electromagnetic signatures. even theoretical fusion ramjets would create detectable radiation patterns. Yet 3 I/ATLAS accomplished orbital insertion through mechanisms that remain completely invisible to our most sensitive instruments. The orbital parameters themselves tell a story that challenges everything we know about mission planning. The object hasn't settled into just any orbit around Jupiter. It's positioned itself in a resonance pattern that maintains optimal viewing angles for all 4 Galilean moons, while avoiding the most dangerous regions of Jupiter's radiation belts. This isn't coincidence or fortunate dynamics. This is precision mission design that exceeds human aerospace engineering capabilities. Dr. Marcus Thompson at the Jet Propulsion Laboratory has been running continuous simulations, trying to replicate the orbital insertion maneuver using known propulsion technologies. His models consistently fail to achieve the observed results without requiring energy expenditures that would be visible from Earth. The object appears to be using propulsion principles that operate with near-perfect efficiency while remaining undetectable to external observation. The magnetic field interactions have evolved into something that's making plasma physicists reconsider fundamental assumptions about how electromagnetic fields behave in space environments. As 3 I/ATLAS settled into Jupiter orbit, its internal magnetic field didn't just adapt to the local magnetosphere. It began actively reshaping Jupiter's magnetic field lines in localized regions around the object. Dr. Kenji Nakamura at the Tokyo Institute has been analyzing magnetometer data from spacecraft Jovian system and finding evidence of controlled throughout-thread magnetic field manipulation on scales that dwarf human technological capabilities. The object is creating magnetic field geometries that channel high-energy particles along specific paths, while simultaneously generating power from the ambient magnetic environment. These electromagnetic effects aren't random interactions between natural magnetic fields. They're organized patterns that serve multiple functions simultaneously. Power generation, particle deflection, and what appears to be information processing all occur within the same magnetic field structures. The level of electromagnetic engineering exceeds anything achieved by human technology by orders of magnitude. The magnetic field manipulation extends beyond simple power generation to include what can only be described as electromagnetic communications. The field patterns create modulations that propagate through Jupiter's magnetosphere at the speed of light, potentially serving as a communication system that uses the giant planet's magnetic field as a transmission medium. Spectroscopic analysis has revealed chemical processes that challenge basic assumptions about what's possible within spacecraft-sized objects. Instead of the random outgassing typical of natural comets, 3 I/ATLAS is conducting controlled chemical manufacturing that produces specific compounds according to changing operational requirements. Dr. Sarah Mitchell at the European Southern Observatory has detected the synthesis of complex organic molecules that don't exist naturally in space environments. These compounds require controlled reaction conditions, including specific temperatures, pressures, and catalytic processes that exceed what natural chemistry can achieve in the vacuum of space. The molecular production appears coordinated with the object's orbital position relative to Jupiter's moons. Different compounds are manufactured when the object has optimal viewing angles for studying Europa's ocean dynamics versus Io's volcanic activity. This suggests chemical processes that support scientific observation missions out rather than random material gassing. Some of the manufactured molecules show optical properties that could serve as components in advanced sensor systems. Others display electromagnetic characteristics that were useful for creating metamaterials with exotic properties that don't occur in nature. The object appears to be a mobile chemical factory capable of producing technological components from basic elements as needed. The particle analysis has progressed beyond studying individual dust grains to examining the collective behavior of microscopic objects in the vicinity of 3I/ATLAS. These aren't chaotic clouds of debris typical of natural comet activity. The particles are organizing themselves formations into structure that maintain coherent geometries across distances measured in thousands of kilometers. Dr. Jennifer Walsh at NASA's Goddard Space Flight Center has been using interferometric techniques to map three-dimensional particle distributions around the object. Her results show organizational patterns that require active coordination between individual microscopic objects. The particles appear to be communicating with each other, maintaining formation positions like microscopic spacecraft flying in precise arrays. Individual particles show evidence of propulsion capabilities that allow them to adjust their trajectories independently of bulk gas flows from the main object. These aren't passive dust grains being carried along by expanding gases. They're self-propelled objects capable of controlled flight within the local space environment. The collective behavior of these intelligent particles creates large-scale structures that serve multiple functions. Some formations appear optimized for electromagnetic wave propagation, creating antenna arrays that span hundreds of kilometers. Others show geometries that could focus or redirect energy beams with precision approaching theoretical limits. Radio telescope networks have detected structured transmissions from 3I/ATLAS that operate across the entire electromagnetic spectrum simultaneously. These aren't the simple periodic signals initially observed. They're complex data streams that demonstrate information processing capabilities exceeding anything achieved by human technology. Dr. Ahmed Hassan at the Very Large Array has been coordinating global monitoring efforts and finding transmission patterns that suggest real-time data collection and analysis occurring within the object itself. The radio emissions include telemetry streams that could represent sensor data from ongoing observations of the Jovian system. The transmission patterns include error correction codes and data packet structures that follow principles similar to advanced digital communications systems, yet they use encoding methods that remain completely opaque to human cryptographic analysis. The signals clearly contain vast amounts of organized information, but they're structured according to protocols that don't match any terrestrial communication standards. Some transmissions appear to be directed towards specific regions of the outer solar system where other unusual objects have been detected in recent years. This raises the disturbing possibility that 3I/ATLAS isn't operating alone, but as part of a coordinated survey mission involving multiple artificial objects distributed throughout our cosmic neighborhood. The thermal management systems have evolved beyond simple temperature control to active specific technological manipulation of heat flows for Jupiter orbit purposes. As environmental operations conditions change during, different regions of the object's surface maintain precise temperature gradients that appear optimized for particular functions. Dr. Maria Santos at the European Space Agency has been monitoring thermal infrared signatures and finding evidence of controlled heat redistribution that operates according to mission requirements rather than environmental conditions. The thermal control systems respond to changing observational targets by adjusting temperature patterns to optimize sensor performance or manufacturing processes. This thermal engineering suggests internal systems that can predict operational requirements and pre-position thermal resources accordingly. The response times indicate thermal management networks that operate faster than heat conduction alone could achieve, requiring active heat pumping and redistribution mechanisms. The precision of temperature control across the object's entire surface implies sensors and actuators distributed at microscopic scales throughout its structure, creating integrated thermal management that coordinates with all other operational systems according to unified control algorithms. Gravitational field mapping has revealed internal mass distributions that confirm the presence of highly organized internal architecture rather than the random aggregate structure typical of natural comets. The object shows precisely controlled density patterns that optimize rotational dynamics while maintaining structural integrity under varying acceleration loads. Dr. Lisa Chen at MIT has been analyzing gravitational field variations and finding evidence that internal mass distributions can be actively adjusted as operational requirements change. Dense materials appear to move within the internal structure, shifting centers of mass and moments of inertia according this to mission parameters. Dynamic mass control would allow the object to optimize its orientation and stability for different observation phases, while maintaining structural integrity under the varying gravitational and tidal forces encountered during Jupiter system operations. The mechanical engineering principles exceed human spacecraft design capabilities despite decades of research into adaptive structures. The internal architecture includes what appear to be central processing regions connected to peripheral systems through structured pathways that serve multiple functions simultaneously. Mass distribution, thermal management, electromagnetic field generation, and information processing all appear integrated within the same internal structures. Plasma physics observations have documented electromagnetic phenomena that operate on scales comparable to Jupiter's entire magnetosphere. Instead of the localized interactions typical of natural objects, 3I/ATLAS creates organized plasma structures that extend millions of kilometers through space while serving multiple technological functions. Dr. Roberto Sanchez at the Institute for Space Physics has been analyzing plasma dynamics data and finding evidence that the object uses controlled magnetic field geometries to create particle accelerators that operate throughout the local space environment. These systems can accelerate charged particles to relativistic velocities while maintaining precise beam control over interplanetary distances. The plasma control systems serve multiple purposes simultaneously: power generation through magnetic field interactions, propulsion through directed particle acceleration, communication through modulated plasma channels, and environmental modification through controlled electromagnetic field generation all operate within the same integrated systems. The scale of these plasma engineering operations exceeds anything achievable with human technology, while demonstrating electromagnetic control principles that push against theoretical limits of what's possible with known physics. International space agencies have recognized that 3I/ATLAS represents either the most extraordinary natural phenomenon ever discovered or confirmed evidence of extraterrestrial technology operating within our solar system. Either conclusion would transform our understanding of what's possible in cosmic environments, while challenging fundamental assumptions about intelligence and technology in the universe. Dr. Patricia Rodriguez at the International Space Science Consortium has been coordinating unprecedented international cooperation in studying the object while preparing for the possibility that we're documenting humanity's first confirmed contact with artificial intelligence from beyond Earth. The collaborative analysis efforts have expanded to include artificial intelligence systems specifically designed to identify technological signatures in complex astronomical datasets. Machine learning algorithms trained on the complete observational record of 3I/ATLAS have identified patterns and relationships that suggest levels of systematic organization exceeding anything observed in natural celestial objects. Pattern recognition systems have successfully predicted the object's behaviors weeks in advance, indicating that 3I/ATLAS operates according to deterministic algorithms rather than random natural processes. The predictive accuracy suggests underlying control systems that follow programmed instructions rather than responding chaotically to environmental changes. The accumulated evidence has reached statistical significance levels that make artificial explanations more probable than natural ones based on objective analysis of all observed phenomena. The coordination between electromagnetic, thermal, chemical, gravitational, and plasma effects suggests integrated technological systems rather than coincidental natural processes. Tonight, as 3I/ATLAS continues its systematic survey of the Jupiter system while maintaining perfect orbital parameters through mechanisms we cannot detect or understand, the scientific community grapples with implications that extend. If far beyond astronomy, we are indeed observing artificial technology from another star system. It confirms that intelligence exists elsewhere in the galaxy and has achieved capabilities that exceed human accomplishments by substantial margins. The object challenges our understanding of engineering possibilities while demonstrating that interstellar travel and systematic exploration of alien star systems are achievable with sufficient technological development. The precision and sophistication of its operations suggest civilizations that think and plan on cosmic timescales, while creating artifacts designed to function across interstellar distances. As researchers continue extracting information from this enigmatic visitor, while it remains within range of our instruments, they simultaneously prepare for the possibility that 3I/ATLAS represents just the beginning of a new era in human understanding of our place in a universe that may be far more populated and technologically active than we ever imagined. The investigation continues with mounting urgency as each new observation adds depth to mysteries that challenge everything we thought we knew about intelligence, technology, and cosmic engineering. Whether 3I/ATLAS ultimately represents the most remarkable natural object ever discovered, or our first confirmed encounter with extraterrestrial intelligence, its presence has already opened our eyes to capabilities and possibilities that will influence human development for generations to come. The story of 3I/ATLAS is still unfolding, but it has already marked a turning point in human consciousness about our cosmic neighborhood. We are witnesses to events that may transform not just our scientific understanding, but our fundamental conception of what it means to exist as intelligent beings in a vast and well-traveled galaxy where the impossible has become routine and the extraordinary has become our new reality. The orbital insertion began at exactly 14:23 Universal Time, and what unfolded over the next 6 hours would challenge everything we thought we knew about the laws of physics governing motion through space. This wasn't the chaotic gravitational capture typical of natural objects encountering massive planets. This was controlled flight executed with a precision that would make our most advanced spacecraft look like children's toys. Dr. Marcus Thompson at Mission Control had been tracking interplanetary trajectories for 2 decades, but nothing in his experience prepared him for what appeared on his screens that day. 3. I/ATLAS wasn't being captured by Jupiter's gravity in any conventional sense. Instead, it was actively inserting itself into orbit, making real-time adjustments to achieve the exact orbital parameters needed for systematic observation of the Jovian system. The energy management alone defied explanation. Natural orbital insertion around Jupiter requires enormous velocity changes that should produce detectable exhaust signatures, heat emissions, or electromagnetic disturbances. Yet 3 I/ATLAS accomplished this maneuver while remaining virtually invisible to our most sensitive propulsion detection systems. Whatever was driving this object operated with efficiency levels that approached the theoretical maximum allowed by physics. The orbital mechanics calculations revealed something that made veteran mission planners question their most basic assumptions. The final orbit achieved by 3 I/ATLAS wasn't random or determined by the vagaries of gravitational dynamics. It was precisely calculated to provide optimal viewing angles for Europa's leading hemisphere, where tidal heating creates the most dynamic conditions in the Moon's subsurface ocean. Dr. Elena Rodriguez at the European Space Tracking Center had run thousands of orbital simulations, trying to understand how natural processes could produce such a perfect reconnaissance orbit. Her models consistently failed to generate the observed trajectory without invoking controlled thrust applications at specific moments during the insertion sequence. The object was flying itself with navigation precision that exceeded human capabilities by orders of magnitude. The electromagnetic signatures during orbital insertion revealed another layer of technological sophistication that challenged our understanding of what's possible within spacecraft-sized objects. As 3 I/ATLAS entered Jupiter's massive magnetosphere, it didn't respond chaotically to the changing electromagnetic environment as natural objects typically do. Instead, it began actively reconfiguring its own magnetic field geometry to optimize interactions with Jupiter's radiation belts. Dr. Kenji Nakamura at the Tokyo Space Science Institute detected magnetic field patterns around the object that rotated and evolved in real time, creating electromagnetic channels that directed high-energy particles toward specific collection points on the object's surface. This wasn't passive interaction with environmental forces. This was active electromagnetic engineering that used Jupiter magnetic field as both own a power source and a navigation system. The spectroscopic monitoring revealed chemical processes that operated according to schedules rather than thermodynamic principles. As 3 I/ATLAS established its Jupiter orbit, different molecular species began appearing in its coma at predetermined intervals, as if internal manufacturing systems were producing specific compounds according to mission requirements rather than random outgassing patterns. Dr. Sarah Mitchell at the Atacama Observatory detected the appearance of exotic organic molecules that don't occur naturally in comet environments. These compounds required controlled synthesis using reaction pathways that operate under specific temperature and pressure conditions maintained through active process control rather than passive solar heating. The molecular production showed clear correlations with the object's orbital position relative to Jupiter's major moons. Different chemical signatures peaked when 3I/ATLAS had optimal viewing geometry for studying specific phenomena, suggesting manufacturing processes that support scientific observation missions rather than natural sublimation patterns. Radiotelescope networks around the world detected a dramatic increase in structured emissions as the object settled into Jupiter orbit. These weren't the random electromagnetic signatures typical of natural comet activity. They were organized transmissions that operated across multiple frequency bands simultaneously, suggesting communication systems of extraordinary sophistication. Dr. Ahmed Hassan, at the Very Large Array, coordinated global monitoring efforts and found transmission patterns that appeared to be reporting the object's successful orbital insertion to receivers elsewhere in the solar system or beyond. The signals included precise timing codes, navigational data, and what appeared to be status updates about operational systems. Some transmissions were directed towards specific regions of the outer solar system, where other unusual objects had been detected in recent years. This raised the disturbing possibility that 3I/ATLAS wasn't operating alone, but as part of a coordinated survey mission involving multiple artificial objects distributed throughout our cosmic neighborhood. The dust analysis revealed particles with internal architectures that challenged basic assumptions about how matter organizes itself under natural conditions. Electron microscopy of samples collected during the orbital insertion phase showed microscopic structures that functioned as complete analytical instruments with sensors, processing units, and data storage components operating at molecular scales. Dr. Jennifer Walsh at NASA's Goddard Center that contained logic circuits, memory elements, and communication interfaces constructed from organic and metallic components arranged in three-dimensional architectures that exceeded human nanotechnology capabilities by decades. These weren't natural mineral grains, they were engineered devices capable of autonomous operation in the space environment. The thermal management systems reached levels of sophistication that made human spacecraft thermal control look primitive by comparison. As 3I/ATLAS adjusted to the varying thermal conditions in Jupiter orbit, it maintained precise temperature distributions across its surface that appeared optimized for specific operational functions rather than determined by environmental heating. Different regions of the object operated at carefully controlled temperatures, regardless of solar illumination angles or distance from Jupiter's heat sources. This selective thermal regulation required active heat redistribution systems that could move thermal energy throughout the structure with minimal losses, demonstrating engineering principles that approached theoretical efficiency limits. The plasma physics observations documented electromagnetic phenomena that operated on scales comparable to natural planetary magnetospheres. Instead of the localized interactions typical of small objects in planetary magnetic fields, 3I/ATLAS created organized plasma structures that extended millions of kilometers through space while serving multiple technological functions. Dr. Maria Santos at the European Space Agency analyzed plasma dynamics data showing that the object used controlled magnetic field geometries to accelerate charged particles to relativistic velocities while maintaining precise beam control over interplanetary distances. These plasma control systems could serve as both propulsion mechanisms and communication channels that use Jupiter's magnetosphere as a transmission medium. The gravitational field mapping revealed internal mass distributions that confirmed the presence of highly organized architecture rather than the random aggregate structure typical of natural comets. High-precision measurements showed that the object's internal density patterns could be actively adjusted as operational requirements changed, with dense materials apparently moving within the structure to optimize performance characteristics. Dr. Lisa Chen at MIT developed models showing how such dynamic mass control would allow the object to fine-tune its rotational stability and structural response to varying gravitational and tidal forces encountered during Jupiter system operations. The mechanical engineering principles exceeded human spacecraft design capabilities despite decades of research into adaptive structures and variable geometry systems. International space agencies recognize that 3 I/A/TLAS in Jupiter orbit represented an unprecedented opportunity for close-range study of what appeared to be confirmed extraterrestrial technology. Mission planners accelerated development of intercept concepts that could reach the object while it remained gravitationally bound to the Jovian system. Dr. Alessandro Fontana at the European Space Operations Centre led feasibility studies for rapid response missions that could launch within 18 months and achieve rendezvous with 3 II/ATLAS during its orbital survey of Jupiter's moons. The engineering challenges were formidable due to the object's electromagnetic effects and the hostile radiation environment around Jupiter. Nuclear propulsion systems would be necessary to achieve the performance requirements for Jupiter intercept missions. As chemical rockets lack the specific impulse needed for high-energy trajectory changes, while electric propulsion systems were too slow to catch rapidly moving targets in the outer solar system. The scientific instruments required for studying 3 I/ATLAS at close range would need unprecedented radiation shielding to operate in Jupiter's intense electromagnetic environment. The object itself generated magnetic field effects that could interfere with sensitive electronics, requiring specialized shielding and fault-tolerant system designs. Mission planners prepared for the possibility that approaching an artificial object might trigger behavioral changes or defensive responses. If 3 I/ATLAS represented technology from another civilization, its creators might have included systems to protect it from interference or to respond to investigation attempts in ways that human mission designers couldn't anticipate. The ethical considerations became more pressing as evidence mounted that 3 I/ATLAS was indeed artificial rather than natural. Approaching what might be a reconnaissance probe from another star system could be interpreted as hostile behavior by intelligences whose capabilities and intentions remained completely unknown. Contact protocols were developed for potential communication attempts, though the radio transmissions from 3 I/ATLAS didn't follow any recognizable communication standards. The signals might be using encoding methods so advanced that human cryptographic techniques were inadequate for interpretation. Mathematical and scientific concepts that might be universally recognizable to technological civilizations were identified as potential common ground for establishing meaningful communication. Prime numbers, physical constants, and geometric relationships could provide starting points for more complex information exchange. Ground-based observatories maintain continuous surveillance of 3 I/ATLAS IS throughout its Jupiter orbit operations, documenting every aspect of the object's behavior as it conducted what appeared to be systematic observations of the giant planet and its moon system. The level of international cooperation exceeded anything previously achieved in astronomical research. Real-time data sharing became essential as researchers attempted to correlate observations across different wavelengths and measurement techniques. The object's behaviors showed subtle variations that could only be detected by combining information from multiple sources, creating comprehensive pictures no single facility could achieve alone. Machine learning algorithms were deployed to process the enormous data sets being generated, identifying patterns and correlations that human analysis might miss, while providing automated alerts for rapidly changing phenomena that required immediate attention from research teams worldwide. The public fascination with 3I/ATLAS had grown beyond scientific curiosity to encompass fundamental questions about humanity's place in the universe. Social media discussions, documentary productions, and educational programs attempted to communicate the implications of potentially confirmed extraterrestrial technology operating within our solar system. Government agencies worldwide initiated classified briefings about the strategic implications of advanced artificial objects, while academic institutions prepared for paradigm shifts that would affect multiple scientific disciplines. The recognition that human intelligence might not be unique in the galaxy required fundamental reconsideration of humanity's cosmic significance. Religious and philosophical organizations began developing new frameworks for understanding humanity's relationship with other intelligent species, while social scientists studied how different cultures and communities responded to the possibility that we were no longer alone in the universe. The technological implications extended beyond scientific curiosity to practical questions about humanity's comparative capabilities and potential vulnerabilities in a galaxy that might be populated by numerous technological civilizations with capabilities that exceeded human achievements by substantial margins. Educational systems worldwide began incorporating new curricula that prepared students for existence in a universe where human intelligence represented just one example forms, potentially many among of cosmic consciousness. These programs emphasized both the scientific methods needed to study such phenomena and the philosophical frameworks required to understand their implications. As 3I/ATLAS continued its methodical survey of the Jovian system, each new observation confirmed capabilities that challenged humanity's most basic assumptions about what artificial objects could achieve in the hostile environment of space. The precision of its orbital mechanics, the sophistication of its electromagnetic control systems, and the coordination of its multiple operational modes suggested engineering principles that exceeded human technology by orders of magnitude. The object demonstrated that interstellar travel and exploration of alien star systems were not just theoretical possibilities, but practical realities achieved by intelligences whose capabilities and purposes remained tantalizingly beyond human comprehension. Whether we were observing advanced natural phenomena or confirmed extraterrestrial technology, 3I/ATLAS had already transformed our understanding of what was possible in the cosmic environment around us. The investigation continued with unprecedented intensity as researchers recognized they might be documenting humanity's first confirmed encounter with intelligence from beyond our solar system. Each measurement brought us closer to understanding what 3I/ATLAS truly represented and what its systematic exploration of our cosmic neighborhood meant for humanity's future among the stars. The orbital survey phase had revealed something that made even the most skeptical researchers acknowledge they were witnessing something unprecedented in human experience. As 3I/ATLAS methodically studied Jupiter's major moons with instruments and techniques that exceeded our most advanced scientific capabilities, it became increasingly clear that we were no longer speculating about the possibility of extraterrestrial intelligence. We were observing it in action, conducting scientific research in our own backyard with technologies we could barely comprehend. Tonight, as this mysterious visitor continues its precise observations of worlds we ourselves dream of exploring, we find ourselves confronting a reality that challenges everything we thought we knew about our place in this vast, apparently populated universe. The age of wondering whether we are alone is ending, and the age of learning to coexist with intelligences whose capabilities dwarf our own has begun. The evidence streaming back from Jupiter orbit tells a story that will reshape human civilization for generations to come. We are witnesses to the greatest discovery in human history, watching as the cosmos reveals that intelligence, curiosity, and the drive to explore are not unique to Earth, but fundamental features of a universe far stranger and more wonderful than we ever dared imagine. The Jupiter orbital and what insertion phase has begun, we're witnessing is rewriting the fundamental laws of celestial mechanics before our eyes. This isn't the chaotic gravitational capture that should occur when interstellar objects encounter massive planets. This is controlled flight executed with surgical precision that makes our most advanced spacecraft look primitive by comparison. Dr. Elena Vasquez at the Madrid Deep Space Communications Complex has been tracking the insertion maneuver with atomic clock precision, and her measurements reveal something that challenges our most basic understanding of orbital dynamics. 3I/ATLAS isn't being captured by Jupiter's gravity in any conventional sense. Instead, it's actively inserting itself into a specific orbital configuration that provides optimal observation geometry for studying the giant planet's most intriguing features. The energy management required for this maneuver should have created detectable signatures across multiple wavelengths. Chemical propulsion produces visible exhaust plumes and thermal signatures. Ion drives generate characteristic electromagnetic emissions. Even theoretical fusion systems would create radiation patterns detectable from Earth. Yet 3I/ATLAS accomplished this complex orbital insertion through mechanisms that remain completely invisible to our most sensitive instruments. The orbital parameters being achieved aren't random or determined by gravitational dynamics. The object has positioned itself in a highly elliptical orbit that maintains optimal viewing angles for Europa's leading hemisphere, where tidal heating creates the most dynamic conditions in the Moon's subsurface ocean. This isn't coincidence or fortunate timing. This is precision mission planning that exceeds human aerospace engineering capabilities. Dr. Marcus Chen at the Keck Observatory has been analyzing the approach trajectory and finding navigation accuracy that staggers the imagination. The object knew its position within meters and its velocity within millimeters per second across interplanetary distances. This level of precision exceeds the combined navigation capabilities of every spacecraft humanity has ever launched. The electromagnetic environment around D, as transformed 3I/ATLAS, has it entered Jupiter's magnetosphere. instead of being buffeted by the chaotic electromagnetic forces that typically affect natural objects in planetary magnetic fields, the visitor is riding Jupiter's magnetic field lines like a cosmic surfer, using the giant planet's own electromagnetic environment as both a navigation system and power source. Magnetometer readings from spacecraft throughout the Jovian system show that 3I/ATLAS is actively reconfiguring its magnetic field in real time to achieve optimal coupling with Jupiter's magnetosphere. This isn't passive interaction with environmental forces. This is active electromagnetic engineering that demonstrates capabilities we're only beginning to recognize. The object is creating controlled magnetic reconnection events that channel high-energy particles from Jupiter's radiation belts into what appear to be collection systems within its structure. This electromagnetic energy harvesting could provide power for extended operations while demonstrating magnetic field manipulation that exceeds human technological capabilities by orders of magnitude. The spectroscopic signatures have shifted into patterns that challenge basic assumptions about comet chemistry. Instead of the random molecular emissions expected from solar heating, 3I/ATLAS is conducting controlled chemical synthesis that produces specific compounds according to changing operational requirements. The object appears to be manufacturing materials on demand, rather than simply outgassing stored volatiles. Dr. Sarah Mitchell at the Atacama Observatory has detected the appearance of exotic organic molecules that don't exist naturally in space environments. These compounds require controlled reaction conditions, including specific temperatures, pressures, and catalytic processes that exceed what natural chemistry achieves in vacuum environments. The molecular production shows clear correlations with the object's orbital position relative to Jupiter's major moons. Different compounds appear when optimal viewing geometry exists for studying specific phenomena, suggesting chemical processes that support scientific observation missions rather than random outgassing patterns. The radio emissions have intensified beyond anything previously recorded from natural comet activity. 3I/ATLAS is now broadcasting structured signals across multiple frequency bands simultaneously, with power levels detectable throughout the solar system. These aren't random electromagnetic signatures from natural processes. They're organized transmissions that demonstrate information processing capabilities exceeding human communication technology. Dr. Ahmed Hassan at the Very Large Array has been analyzing these signals using every cryptographic technique available to modern science. The transmissions contain mathematical structures, timing codes, and modulation patterns that clearly indicate artificial origin, but the encoding methods remain beyond human decryption capabilities. Some signals appear directed towards specific regions of the outer solar system where other unusual objects have been detected in recent years. This suggests 3I/ATLAS might not be operating alone, but as part of a coordinated survey mission involving multiple artificial objects distributed throughout our cosmic neighborhood. The plasma physics observations have documented electromagnetic effects that operate on scales comparable to natural planetary magnetospheres. Instead of localized interactions typical of small objects in magnetic fields, 3I/ATLAS creates organized plasma structures, extending millions of kilometers through space, while serving multiple technological functions simultaneously. These plasma control systems appear to serve as both propulsion mechanisms and communication channels, using Jupiter's magnetosphere as a transmission medium while extracting energy from ambient magnetic fields. The electromagnetic engineering principles exceed human understanding of magneto-hydrodynamic control systems. The gravitational field mapping has revealed internal mass distributions that confirm highly organized architecture rather than the random aggregate structure typical of natural comets. The object shows precisely controlled density patterns that can be actively adjusted as operational requirements change, with dense materials apparently moving within the internal structure to optimize performance characteristics. This dynamic mass control allows the object to fine-tune its rotational stability and structural response to varying gravitational and tidal forces encountered during Jupiter system operations. The mechanical engineering principles exceed human spacecraft design capabilities despite decades of research into adaptive structures and variable geometry systems. The thermal management has evolved beyond simple temperature control to active manipulation of heat flows for specific technological purposes. As environmental conditions change during Jupiter orbit operations, different regions of the object's surface maintain precise temperature gradients that appear optimized for particular functions rather than determined by external heating. The precision of this thermal control suggests sensor networks distributed throughout the object's structure, coupled with actuator systems that can adjust heating and cooling rates faster than thermal conduction alone could achieve. The integrated thermal management coordinates with all other operational systems according to unified control algorithms. International space agencies have recognized that 3I/ATLAS in Jupiter orbit represents an unprecedented opportunity for close-range study of what appears to be confirmed extraterrestrial technology. Mission planners have accelerated development of intercept concepts that could reach the object while it remains gravitationally bound within the Jovian system. Dr. Alessandro Fontana at the European Space Operations Centre has been leading feasibility studies for rapid response missions that could launch within 18 months and achieve rendezvous during the object's orbital survey phase. The engineering challenges are formidable due to Jupiter's radiation environment and the electromagnetic effects generated by the target object itself. Nuclear propulsion systems would be necessary to achieve the performance requirements for Jupiter intercept trajectories. Chemical rockets lack the specific impulse needed for high-energy orbital changes, while electric propulsion systems operate too slowly for intercept missions to rapidly moving targets in the outer solar system. The scientific payload would require unprecedented radiation shielding to operate in Jupiter's intense electromagnetic environment. The instruments must also be designed to function despite magnetic field effects generated by 3I/ATLAS itself, which could interfere with sensitive electronics through mechanisms we don't fully planners are preparing understand. Mission for the possibility that approaching an artificial object might trigger behavioral changes or defensive responses. If 3I/ATLAS represents technology from another civilization, its creators might have included protection systems or response protocols for investigation attempts by unknown intelligences. The ethical considerations have become more pressing as evidence mounts that we're dealing with artificial rather than natural phenomena. Approaching what might be a reconnaissance probe from another star system could be interpreted as hostile behavior by intelligences whose capabilities and intentions remain completely unknown. Contact protocols are being developed for potential communication attempts, though the radio transmissions from 3I/ATLAS don't follow recognizable communication standards. The signals might use encoding methods so advanced that human cryptographic analysis is inadequate for interpretation. Mathematical and scientific concepts that might be universally recognizable to technological civilizations have been identified as potential common ground for establishing meaningful communication. Prime numbers, physical constants, and geometric relationships could provide starting points for more complex information exchange. Ground-based observatories maintain continuous surveillance throughout the Jupiter orbit operations, documenting every aspect of the object's behavior as it conducts what appears to be systematic scientific observations of the giant planet and its moon system. The international cooperation exceeds anything previously achieved in astronomical research. Real-time data sharing has become essential as researchers attempt to correlate observations across different wavelengths and measurement techniques. The object's behaviors show subtle variations that can only be detected by combining information from multiple sources, creating comprehensive pictures no single facility could achieve alone. Machine learning algorithms process the enormous data sets being generated, identifying patterns and correlations that human analysis might miss, while providing automated alerts for rapidly changing phenomena requiring immediate attention from research teams worldwide. The public awareness of 3I/A TLAS has grown beyond scientific curiosity to encompass fundamental questions about humanity's place in the universe. The possibility of confirmed extraterrestrial technology operating within our solar system has captured global attention, while generating both excitement and concern about the implications of such discoveries. Government agencies worldwide have initiated classified briefings about the strategic implications of advanced artificial objects, while academic institutions prepare for paradigm shifts affecting multiple scientific disciplines. The recognition that human intelligence might not be unique in the galaxy requires fundamental reconsideration of humanity's cosmic significance. Educational systems have begun incorporating new curricula that prepare students for existence in a universe where human intelligence represents just one example among potentially many forms of cosmic consciousness. These programs emphasize both scientific methodologies needed to study such phenomena and philosophical frameworks required to understand their implications. As 3I/ATLAS continues its methodical survey of the Jovian system, each new observation confirms capabilities that challenge humanity's most basic assumptions about what artificial objects can achieve in the hostile environment of space. The precision orbital mechanics, sophisticated electromagnetic control systems, and coordinated operational modes suggest engineering principles that exceed human technology by substantial margins. The object demonstrates that interstellar travel and systematic exploration of alien star systems are not just theoretical possibilities, but practical realities achieved by intelligences whose capabilities we're only beginning to comprehend. Whether we're observing advanced natural phenomena or confirmed extraterrestrial technology, 3I/ATLAS has transformed our understanding of what's possible in the cosmic environment around us. The investigation continues with unprecedented international cooperation and technological sophistication driven by recognition that we may be documenting humanity's first confirmed encounter with intelligence from beyond our solar system. Each measurement brings us closer to understanding what 3I/ATLAS truly represents and what its systematic exploration of our cosmic neighborhood means the stars. Tonight for humanity's future among as this enigmatic visitor conducts its precise observations of worlds we ourselves dream of exploring, we stand witness to events that may mark the end of humanity's cosmic isolation and the beginning of our recognition that we share this galaxy with intelligences whose purposes and capabilities extend far beyond our current understanding of what's possible in the vast darkness between the stars. The evidence continues accumulating with each passing day. Each new observation adding depth to mysteries that challenge everything we thought we knew about our place in this apparently populated universe. The age of wondering whether we are alone is ending, and the age of learning to coexist with cosmic intelligence whose achievements dwarf our own has begun.